Hello everyone. First, let me introduce myself. I am Duong Tien Trung from Busan National University. Today, I am going to review the paper Evaluation of the Pressure Field on a rigid body entering a quiescent fluid through particle image velocimetry by Riccardo Panciaroli and Maurizio Porfiri. The presentation is divided into 5 parts. First one is the introduction. The second one is the theoretical background. In this section, I'm going to do the velocity-based pressure evaluation and the Wagner's analytical solution. The third one is the experiments. The fourth one is the experimental results. And the final one is the conclusions. The estimation of the hydrodynamic loading during the slamming is a major scientific and engineering challenge, which has attracted the interest of several researchers over the years. The evaluation of the hydrodynamic loadings is currently restricted to the direct measurement of the pressure field at specific locations through pressure gauges mounted on the slamming structure. The technical advancements in high-speed and high-resolution image acquisitions have enabled the use of the particle image velocimetry records to indirectly measure the hydrodynamic pressures. The main objective of this study is to demonstrate the feasibility of the PIV-based pressure measurements from Navier-Stokes equations in the problem of a solid body entering a quiescent fluid. In this section, we describe the methodology used to evaluate the pressure distribution from the velocity field, and we illustrate the analytical solutions used for benchmarking the proposed approach. For a two-dimensional incompressible flow, the Navier-Stokes equations can be used to indirectly compute the instantaneous pressure gradients from the instantaneous velocity and the material acceleration. The pressure fields is then obtained by integrating the pressure gradients with boundary conditions set on a part of the contour of the Select domain. The figure 1 depicts the main elements of the spatial integration process. We initially select a point on a water-free surface, point A, where the pressure is set to 0 using a simple forward integration along the vertical boundary E1 and the horizontal boundary E2. We calculated the pressure field therein. From the knowledge of the pressure on the E1 and E2, we compute the pressure field in the whole integration region by following the spatial eroding scheme by Bohr and Konterger 1999 in the figure 2. The analytical solution developed by Wagner 1932 allows for predicting the impact dynamics of a rigid body entering a quiescent water surface. Within this framework, the velocity and acceleration of the impact wedge are given by equation 3a and 3b. From the wedge motion, the approach of Wagner allows to compute the pressure distribution through equation 4. The experiment apparatus, schematically shown in the figure 5, is composed of an aluminum frame suspending a transparent tank with the length, the width, and the depth. You can see in this table. And the tank is filled up to the 300 millimeters to prevent the water overflow after impact. The laser source is positioned at the bottom of the frame below the tank, and its location is adjusted to illuminate the wedge along its middle span and thus minimize the three-dimensional phenomena. Experiments are performed on a wedge with 25-degree right angle falling from 25, 15, and 75 centimeters. The specimen's dimension you can see in the table here. The two-dimensional PIV system comprises a ray-powered laser source and a phantom CCD camera. The spatial resolution is shown in this table, and the acquisition frequency is 4 kHz. The hollow glass spheres of 10 micrometers mean diameter are used as a seeding in the PIV study. The dimensions of the field of view are approximately 130 mm by 64 millimeters. The PIV analysis is executed using an FFT-based cross-correlation using a multi-grid approach with decreasing the intercorrelation area from 34 by 34 to 16 by 16 pixels. A 2 by 3 Gaussian subpixel interpolation scheme is utilized for subpixel resolution, and the interpolation window is advanced with the 50% overlap. To ascertain the reliability of the experimental setup and the ability of the acquisition system to record the wedge kinematics, it is needed to compare the acceleration of the falling wedge obtained from the Wagner's theory with the experimental observations. Figure 7 compares the time trace of the acceleration over the impact time of the rigid wedge falling from 25, 50, and 75 centimeters with the Wagner's solution in equation 3b. Results reported in figure 7 indicate a good agreement with the experimental results and theoretical findings from the Wagner's solution, thereby providing some verification of the experimental setup and data acquisition system. Figure 8 compares the velocity of the wedge measured using the excited probe analysis with the PIV measurement in the proximity of the keel. The PIV measurement underestimates the fluid velocity at the initial instance of the impact. However, as the time increases, the PIV measurement tends to approach the wedge speed. As anticipated, none of the PIV measurement in Figure 8 indicated a fluid velocity higher than 2 meters per second. Figure 9 displays the indirectly measured pressure field for the free falling height computed for several instants during the impact. The experimental results demonstrate that the pit pressure is located where the water piles up on the wedge. From the location of the pit values, the pressure sharply reduces in every direction with a trend that is almost inversely proportional to the distance from the pit location, and is known for the free surface. Figure 10 compares the PIV predictions with theoretical findings from equation 4, and a sequence of the time incidents in the vicinity of the one depicted therein. Figure 10 demonstrates that a remarkable agreement between the experimental results and analytical solution along the whole wedge length of the wedge. A quantitative comparison between the experimental results and theoretical predictions is performed by computing the error defined by equation 6. The error is less than 4.1%. Figure 11 compares the pit and the minimum pressures for the three entry velocities with the theoretical predictions. The experimental results for the three experiments almost collapse on one same line, supporting the robustness of the PIV-based pressure measurement to variations in the impact speed. The experimental results also shows that the minimum pressure is in very close agreement with the analytical solutions. On the other hand, the agreement for the pit pressure is initially only between 20%, while it improves as the wedge further penetrates the surface. Figure 12 confirms the accuracy of the PIV-based indirect force measurements in water entry problems. PIV-based measurements are found to be in close agreement with both theoretical results from Wagner's solution and the experimental findings based on the measurement of the wedge accelerations. In conclusion, this paper shows the feasibility of non-intrusively measuring the hydrodynamic pressure experienced by a rigid body entering the water from the PIV data. The pressure field is computed by solving the two-dimensional incompressible Navier-Stokes equations with the flow kinematics estimated from the PIV data. The results demonstrate the robustness of the PIV-based pressure measurement, provided that the hydrodynamic pressure over the wet surface of the wedge is accurately reconstructed. So this is the end of my presentation, and thank you very much for your attention.